So for this chapter, we're going to be doing something that seems like it's sort of out of the middle of nowhere and doesn't really have a whole lot of application for what we've been doing since we just finished talking about equilibrium. But it has a specific point, and that is what to do in the situation that we have when we have a distributed load. And so what do I mean by that? So I mean, let's take a beam, and that beam looks like this. Oops. All right, so it's got a couple of, it's not a very good one, but that's whatever you can see. So a beam with a couple of couple of supports, a normal fixed pin support over here and a roller support on that side. And then we have a load that is continuous and distributed across the entire beam, and it has some function x right there. Okay, so we know what to do with this if there's a single beam there, but a single load. But if we've got a multiple loads, we sort of end up with the problem. How do we draw the free body diagram? So let's draw the free body diagram over here of the system, right? So we've got a reaction over at AY, a reaction in AX, right? And then one pointing just up for the roller support at B. So we'll call that, of course, A and B. But then what do we do with this? So we don't know what to do with this distributed load right now. There's no way for us to write this as a single point. And so what we want to do is come up with a mathematical way to say, what I want to know is let's pick a point, let's say A, and then we want to be able to take this entire action of this force, Wx, or this distributed load, Wx, and replace it with a single force acting downward. So something like this, W acting at some sort of distance, X, and we'll call it bar. And we'll do that for a reason that'll become obvious in a little bit. All right, so we've got these two things. So the question is how do we get from here to here? And how do we find what X bar is and what W is? All right. So the way that we do this comes from let's start over with that. Comes from a question about the distribution of mass in a 2D body. So let's say we've got some sort of random 2D body right there, and we want to ask the question, this 2D body, basically the weight generates a moment, and we're thinking just a thin plate, so it looks something like this. So generates a moment, in this case the weight, right, because the weight's going to act downward somewhere. We don't know where, but the total weight W is going to act downward through some point. And what we want to do is we want to figure out where that point is. And so we ask the question, this weight tends to cause rotation about the x-axis and about the y-axis, right? Not about the z-axis. And that's because this weight is all pointing downward. Let me get rid of those. All right. So what we're going to do is what we really want to know is we want to say this is located, the total weight acts at some point X and Y, and it acts downward. And so how do we figure out how to calculate this moment of the weight about this whole point? Well, what we do is what you might expect. We take a little chunk of the material that has a differential weight, right? Very scary differentials. You'll get over it. And it acts at some distance Y and some distance X. And what we can think of is, well, if we've got each one of these differential weights, we can just sum it up, right? So we have x1 dw1 plus x2 dw2 plus so on, so on, so on. Same thing with the y, right? y1 dw1 plus y2 dw2 and so on. All right. So that makes a lot of sense. So basically all we're doing here, right, is we're finding the resultant of x times dw1, x times dw2, basically resultant of all the moments generated by all the tiny little pieces of the material around the y-axis in this case, right, and around the x-axis. And we call these the first moments. And so this one Q sub y, right, because that if you're a distance x away, you're generating a moment about the y-axis, and this is q sub x. For the same reason that generated a moment about the y-axis, this generates a moment about the x-axis. So these are known as first moments. And that there's a first moment implies that there's a second moment and maybe even a third moment. In engineering, we really stop the second moment, and we will talk about that later in a later chapter. All right. So what can we do with these? Well, these moments, I'm going to get rid of these, but leave a little picture there. That sum, or that sort of series sum that we had right there, we because we're engineers, are going to basically just say, since those are all differentials, we can write this. And then integral of y dw, right? So we replaced all those sums with those integrals. And that's what we did there. And since we're also in 2D, right? This is a 2D plate. We can say something about the weight. So the weight is going to be equal to the density times the thickness of the plate times the area of the plate, right? So that should make a lot of sense, right? Because that's the density and this is the volume of the plate. All right. So we can rewrite this using that information and get x, right, thickness rho area equals integral of x, thickness rho, and now we replace the dw with a dA. Same thing with the y, thickness, density, area, total area of the plate equal to y, thickness, density, and area again. All right, and then we can just cancel, right? So these two will cancel because they're constant thickness plate. And we're left with, finally, a relationship for x times big A and y times big A equal to the integral of x dA and y dA. All right, so there we go. So these are our first moments. Sorry, a little wonkiness there. First moments of a plate. All right, of uniform thickness. All right, so we've got these two pieces. So that's great. So now we have these equations. This XA and this YA are called special. These big X's and big Y have a special term, and this is called the X location of the centroid and the Y location of the centroid, right? Because this is the effective location where all of the weight of the plate acts, and this is the effective location where all the weight of the plate acts with respect to the Y-axis. So these two first moments help us figure out the centroid, also known as the center of gravity for these particular materials. All right, so that's how we calculate it. You'll use these integrals later on. We won't do it in this section right now, but what we'll do for this section is a thing called composite. So what we'll do is we'll go back to the sort of sum idea. So composite areas, and this is useful for composite. Need to know there. Sorry. This is useful for cross sections or shapes or areas that are made up of pieces. So, for example, we could consider this 2D piece, x and y axis, made up of a square with length, with two sides, right? Length A, and then another side, length B, and then perhaps it has a hole. And so we've just got sort of this area right here. And this has radius r. All right. So the way that we would do this is we would say, all right, well, our x is equal to the sum of all the areas, right? Because this is that total area, A. And then it's equal to a sum of all the centroids of all the little individual areas. So so we've got two regions. We've got region 1 here and region 2 here. And what we'll do is we'll sum up the areas of this region. This is a whole, right? So the area actually turns out to be negative because it doesn't exist. And this one is just basically the area of a square. And then we have the centroids location of each of the pieces, right? So the location of the centroid of the circle is right in the middle. And again, also the location of the centroid of the square is right in the middle. And then if these are two coincide, then they're exactly the same. We can do the same thing for y. And then equal the sum of the y, the first moment of all the pieces, right? So the first moment of the total area, this value right here, is equal to the sum of the first moments of all the other pieces. Keeping in mind that y bar is from your area of interest, or sorry, your reference point. So in this case, right, almost always the origin, and so our R location is here. So that's our x bar for 2. It's also our x bar for 1 because they happen, this is in the center, and then the center is also on the square. All right. There's a whole bunch of tabulated shapes in your book, and you can go and look them up from there. And that's pretty much it for composite areas. Thanks.